Hello, I'm Bob Raphael, Operations Program Manager for the X-33, and this is the factory floor at Lockheed Martin Skunk Works, where we're getting ready for the first flight of the X-33. The X-33 technology demonstrator is being developed by Lockheed Martin Skunk Works under a cooperative agreement with NASA. The X-33 will pave the way for a commercially developed, reusable space plane that Lockheed Martin calls VentureStar. The VentureStar will reduce the cost of launching payloads into space from $10,000 to $1,000 per pound. In this program, we'll show you some of the critical activities going on across the country, activities that will take the X-33 from concept to flight test. We'll also show you some of the recent milestones we've met in manufacturing and assembly. What you see here in the background is the liquid oxygen tank, delivered in February of this year. Its complex shape consists of multiple sections welded together to form much of the nose and forward third of the X-33. In fact, it's designed to carry structural loads as well as more than 181,000 pounds of liquid oxygen. The oxygen tank was designed, built, and tested by Lockheed Martin Michoud Space Systems in a record 21 months. Technicians are now installing plumbing and wiring on it, in addition to the attach points which will connect the X-33's thermal protection system. The thermal protection system is another key technology the X-33 will demonstrate. When VentureStar is built, its thermal protection system will safeguard it from re-entry temperatures as high as 2,600 degrees Fahrenheit. Unlike most thermal protection systems, where the insulation material is mounted on the outside of the vehicle, X-33's thermal protection system is the vehicle's aerodynamic structural shell. Testing in NASA's Langley Research Center high-temperature wind tunnel verified the integrity of aeroshell thermal protection system when subjected to winds at a temperature of 2,000 degrees flowing onto the structure at 7 times the speed of sound. Thermal protection materials were also flight tested on an F-15B at Dryden's Flight Research Center to demonstrate the design's abilities to withstand unsteady supersonic flows and shock waves. Metallic tiles, soft reusable surface insulation tiles, and sealing materials were subjected to speeds up to Mach 1.4 and an altitude of 36,000 feet. As expected, material showed no signs of wear or damage. Part of the thermal protection system consists of Inconel and titanium panels that will be attached to the lower half of the vehicle. There are also 17 blanket insulated composite panels that will be attached to the top half of the vehicle. Fit checks were conducted in September that demonstrated the ease of installation and removal. This is the key to the system's designed for maintenance and reduced operations cost and time. The final thermal protection system durability test was completed October 1st at Marshall Space Flight Center. The thermal protection system withstood 60 missions, that's 4 times the flight test exposures expected on the X-33. Engineers at Stennis Space Center in Mississippi recently conducted the first of 18 tests on the power pack, a main component for the X-33 engines being built by Boeing Rocketdyne. It's the power pack that supplies the liquid oxygen and hydrogen to the Aerospike engine's powerful thrusters. The recent test is a critical milestone in the development of the engine. The test was designed to calibrate the liquid hydrogen and liquid oxygen fuel turbopumps. It's also verified valve timing for priming the gas generator. The thrust chambers for the X-33 were recently fabricated and have completed qualification. There are 8 thrusters built by GenCort Aerojet, and they form the reaction control system. By firing one or more of these thrusters, the X-33 can achieve the maneuvers it needs to make in its descent. Aerojet used a high-temperature alloy called columbium for the thrust chambers, only 2 months after determining the original material, Haynes 188, lacked the thermal capacity required. This quick turnaround illustrates the determination of the X-33 team to meet the technical challenges intrinsic with this program. The components for the 2 composite liquid hydrogen tanks manufactured by Alliant Tech Systems have been shipped to Lockheed Martin Missiles and Space for final assembly and curing. Alliant took on a major technical challenge in building components of this proportion that could prevent the seepage of liquid hydrogen molecules. Next stop for the tanks, NASA Marshall Space Flight Center for testing. We've only been able to talk about a few of the many milestones already met for the X-33. More on other milestones next time as the countdown continues.